Okay, here we are with section 9.2, hypothesis test for a population mean when the standard deviation is known. So again, you're going to see in these sections that there are going to be conditions to each section, whether it's known or unknown. So once again, 3x5 cards, creating a flow chart might be the best thing to do. Maybe I'll make that an assignment also, so that can help you keep track. So let's take a look at performing hypothesis tests with the critical value method, performing the test with the p-value method, describing the relationship between a hypothesis test and the confidence intervals, describing relationship between little alpha and the probability of the error, report the p-value or the test statistics value, and distinguish between statistical significance and practical significance. So, performing a hypothesis test with a critical value method. There are two ways to perform hypothesis tests. Both methods produce the same results. They are the critical value method and the p-value method. In a hypothesis test, the idea is to select calculated statistics such as X mean, compare it to the value in the null hypothesis, H sub 0. If the difference between the sample mean and the value in the null hypothesis is large, it's less likely to be due by chance, and the null hypothesis is likely to be true. Otherwise, a small difference might be due to chance, and the null hypothesis may as well be true. Oh, less likely to be true. Okay, so we're going to have to determine how strong the disagreement is in the sample mean and the null hypothesis. If it's large, less likely to be true. If it's small difference, likely to be true or may be true. So we begin with an example. The College Board reported in a recent year that the mean math was 515 with a standard deviation of 116. The results in an earlier study suggest that coach students would have a mean of SAT score of approximately 530. A teacher who runs an online coaching program thinks students coached by his method have a higher mean than this. So he believes that the mean score for his students is greater than 530, then a null hypothesis would be 530, and the alternate hypothesis would be greater than 530. So now suppose a teacher draws a random sample of 100 students who are planning to take the SAT and enrolls them in the online coaching program. After completing the program, the sample mean SAT score is 562. This is higher than the null hypothesis, but to determine how strong the disagreement is between the sample mean and the null hypothesis, we have to calculate the test statistic, which is just the z-score of the sample mean. So assuming that the population standard deviation is 116, the test statistic mean would be our 562 minus our null hypothesis, which was the mean, divided by 116 divided by the square root of 100, which would be 10. And there's a division sign missing here. Again, oh my goodness, these slides. I'm going to have to go overhaul them. All right, so here we have our result is 2.76. So visually we can see from the figure that our observed value of 562 is over here when we know about our standard deviation. So it's pretty out in the tail distribution, far from the null hypothesis. Intuitively, it appears that it's pretty evident against the null hypothesis and that the teacher is correct. The critical value method is based on the idea that we should reject the null hypothesis if the value of the test statistic is unusual when we assume the null hypothesis to be true. we choose a critical value which forms a boundary between the values that are considered unusual and the values that are not. The region that contains the unusual values is called the critical region. If the value of the test statistic is in the critical region, then we can reject the null hypothesis. The probability that we use to determine whether an event is unusual is called significance level. The significance level is denoted by alpha. Therefore, the area of the critical region is equal to alpha. The choice of alpha is determined by how strong we require the evidence against the null hypothesis to be in order to reject it. The smaller the value of alpha, the stronger we require the evidence to be. There'll be some examples here coming up. So, one of the most commonly values used for alpha is 0.5. So when alpha is 0.5, we use a one-tailed test, and the critical value is 1.645. How did we get that? Well, by now we should know that if our alpha is 5% here, that's 5% here and 5% here, which leaves 90% left in the center. And our z value for 90% is 2.76. Okay, so, and our critical value for that number is 1.645. So we have all this information over here. So we conclude that the mean SAT math scores for students completing the online coaching program is in fact greater than 530. So again, we're going to recall that our z-score of 2.67 falls in this critical region. It's over here in this critical region. So since it does fall in the critical region, we're going to say that the online coaching program does in fact help more than 530 score. So let's take a look again. We have a left-tailed test, and that would be to the left of it. We have a right-tailed test to the right of it. And then we have a two-tailed test, which could be either here or there. In other words, it doesn't fall in this region. It falls on one way or the other. So you have left-tailed, right-tailed, and two-tailed. The table will indicate the critical values for some commonly used significant levels, and these we've gone over before, but it's good to look at them again. We have our left-tailed, negative 1.282. We have our right-tailed, which would be positive 1.282, and that's for our 0.1. And we have our two-tailed, which is going to be plus or minus 1.645. At our 5%, our one-tailed would be 1.645, 1.645 positive for the right-tailed. And then if I were to take 5%, both sides combined, that's actually going to be 95% left in the middle. And then that's why we get our 1.96. Now, if we want to take a look at 0.02, we'll use these values, 0.01, which will use these values. Now, the most common ones are 0.05 and 0.01. And you got to have a lot of evidence to have 0.01. All right, so let's assume for performing the hypothesis test about the mean when the standard deviation is known, that we do have a simple random sample, and that the sample size is large, which means bigger than 30, or the population is approximately normal. So here we have the American Automobile Association reporting that the mean price of a gallon of regular grade gasoline in the city of Los Angeles in January 2017 was $2.82. Now, a recently taken simple random sample of 50 gas stations in Los Angeles had an average price of 2.77 cents. Now let's assume the standard deviation of the prices is 15 cents. An economist is interested in determining whether the mean price is less than $2.82. So he's going to use the critical value method to perform a hypothesis test of 0.05. So again, we're saying it doesn't necessarily have to be exactly $2.82. We want to know if it's significantly different than that. And that's why we have this level that we're going to test it on. First, we check the assumptions. It is a simple random sample, and the sample size is large. The assumptions are met, so the null and alternate hypothesis are mean is 2.82. That's our null, and we want to see if it is greater than 2.82. That is what the economist is looking at now. We actually want to see if it's less than, not greater than. This is another mistake. Oh, this is starting to get really annoying. Okay. So here we have a significance level, and that means since it is a left-tailed test, because we want to go less than, we're going to use negative 1.645. We put in our values for our test statistics, and we get negative 2.36. This is a left-tailed test, so we're going to reject the null hypothesis if z is less than negative 1.645, since 2.36 is less than negative 1.645. We reject the null hypothesis at this level. So we can conclude that the mean price of gasoline, of regular gasoline in Los Angeles, is in fact less than $2.82. Less than. I hope you're making these corrections when I go over them on your notes. If you're not, back up and put that on. Okay. Performing the hypothesis test with the p-value method. P-value is the probability that a number drawn from a distribution of the sample mean would be as extreme or more extreme than our observed value of our sample mean. Unlike the critical value, the p-value tells us exactly how unusual the test statistic is. For this reason, the p-value method is used more often in practice, especially when technology is used to conduct a hypothesis test. The smaller the p-value, the stronger the evidence against the null hypothesis. So again, we have this online coaching program for the SAT. Same thing as we looked at before. We have the sample mean score now. We're saying is 562. We want to take a look at it when the standard deviation is 116. Does this provide a strong enough evidence against the null hypothesis? So the first thing we're going to do is assume always that the null hypothesis is true. So therefore we assume that the mean is 530. So the sample size is large. We know that it's approximately normally distributed. So we have our standard deviation of 11.6. Now our test statistic here is going to be our z-score of our sample mean minus our null hypothesis over the standard deviation divided by, there it's missing again, divided by our 100. Oh, okay, so I guess that's, yeah, divided by, so that would move it back to 11.6. Needs to be a line right here. So visually we can see from the figure that our observed value is, sample mean is 562. It's pretty far out of the tail distribution, far from the null hypothesis, and intuitively it does appear that there's evidence that's fairly strong against the null hypothesis. The p-value is under the normal curve to the right of 2.76. This equals 0.0029 using the table A2 or technology. Therefore, the p-value for this test is 0.0029. Such a small p-value strongly suggests that the null hypothesis should be rejected. Choosing a significance level. So now you've seen the smaller the p-value, the stronger the evidence is against the null hypothesis. Therefore, to make a decision to reject the null hypothesis using the p-value method, we must 1. Choose a significance level that's between 0 and 1. 2. Compute the p-value. If p-value is smaller than or equal to alpha that was chosen, we reject the null hypothesis. If it's greater than it, we do not reject the null hypothesis. So again, if the p is less than or equal to alpha, we're going to say that the null hypothesis is rejected at the alpha level, or that the result is statistically significant at the alpha level. Suppose we found a p-value that was 0.0122. Would you reject it at the 0.05 level? Would you reject it at the 0.01 level? Well, we would reject it at the 0.05 level because it is smaller than that, okay? But 0.122 is larger than 0.01, so we don't reject it at that level. We don't reject it at 0.01 level. Oh my goodness, another mistake. Make that a 1. Okay, so the mean height of an adult man is 69.7 inches with a standard deviation of 3. Sociologists believe that taller men may be more likely to be promoted to positions of leadership. So the mean height mu of male business executives may be greater than the mean height of the entire male population. That's interesting. A simple random sample of 100 male business executives has a mean height of 69.9 inches. Assume that the standard deviation of male executive heights is 3. Can we conclude that male business executives are taller than the average general male population at the alpha equals 0.05 level? So first we check the assumptions. We have a simple random sample and the sample is large. It's greater than 30. So all of our assumptions are satisfied. So now our null hypothesis is that the mean is 69.7 and our alternate hypothesis is that it is greater than 69.7. Because our assumptions are satisfied, we can find our statistic mean normally distributed with our null mean at 69.7 and our standard deviation at 0.3 because we have to divide it by our square root of 100. Our test statistic then would be our 69.9 minus 69.7 all over our 0.3, and we have a 0.67. This is a right-tailed test. So the p-value is the area to the right of z equals 0.67. Using the table or technology, we find that the area to the right of that would be 0.2514. So it's not unusual. It's not smaller than 0.05. So since it is bigger than that, we do not reject the null hypothesis at the 0.05 level. There's not enough evidence to conclude that male executives have a greater mean height than adult males in general. The mean height of male executives may be the same as the mean height of adult males in general. Maybe. 2, a large company, the attitudes of workers are regularly measured with a standardized test. The scores on the test range from 0 to 100, with a higher score indicating greater satisfaction with their job. The mean score over the company's employees was 74, with a standard deviation of 8. Some time ago, the company adopted a policy of telecommunicating. Under this policy, workers could spend 1 day per week working from home. Isn't that interesting? Wonder if anyone would ever work from home. After the policy had been in place for some time, a random sample of 80 workers was given the test to see if their mean level of satisfaction had changed since the policy was put into effect, and the sample mean was 76. Assume the standard deviation is 8. Can we conclude that the mean level of satisfaction is different since the policy changed at the 0.05 level? Now, we know we have a simple random sample. Our sample size is large, so we can set up an alternative hypothesis to be equal to 74 and not equal to two-tailed test. So we have our sample mean approximately normally distributed with a mean of 74, a standard deviation of 0.8944. Our test statistic would be that 76 minus 74 divided by that value. It's a two-tailed test. So the p-value is the sum of the area to the right and to the left. Using A2 or technology, we find these areas to be 0.025. Since p is less than 0.05, we reject the null hypothesis at 0.05 level. We conclude that the mean score among employees has changed since the adoption of telecommunicating. See, now I was going to guess that it really wasn't that big of a difference. I would have been wrong, not the first time. Okay, using a z-test command, perform hypothesis test when the population and standard deviation is known. Again, from the very beginning slide, I said you're going to have to keep track of these. This command is accessed by pressing stat, highlighting the test menu. If the summary statistics are given, the stats option should be selected for the input. If the raw data is given, data option should be selected. So we've done this before. If we have our statistics, we press this. If we have our data, we press this. So here we have that same example with the company's attitudes, and we're going to assume that the standard deviation is still 8. Can we conclude that the mean level of satisfaction is different since the policy changed at the 0.05 level? Yes, we check to see if we have our assumptions and everything's good. So now we need to put it into our calculator. So we go to tests, we select a z-test, we choose statistics, we input our values, we select whether it's right-tailed, left-tailed, or two-tailed, and it's two-tailed, and we press our value and we see that it is in fact supporting what we got when we did it by hand. Describing the relationship between hypothesis tests and confidence intervals. Here we rejected the null hypothesis at 74 at alpha equals 0.05. In doing so, we're saying that 74 is not a plausible value for the mean. Another way to express the information about mu is through a confidence interval. If we construct a 95% confidence interval for mu, the attitude of the workers we find will be between 74.247 and 77.753. Now, see how this interval does not include the 74 that we started with? The confidence interval is what can tell us and support some more that 74 is not a plausible value since we changed our system. Okay, describing the relationship between alpha and the probability area. So we looked at type 1 errors occur if we reject the null hypothesis when it is true, and type 2 occurs when we do not reject the null hypothesis when it is false. We can make the probability of these errors small. The probability of a type 1 error is equal to the significance level, which is denoted by alpha. In other words, if we perform a test at the significance level of 0.05, the probability of making a type 1 error is 0.05. Because alpha is the probability of the type 1 error, why don't we always choose very small for alpha? Well, the reason is the smaller the value for alpha, the larger the value for beta, the probability of making a type 2 error. Report the p-value and test statistic value. Sometimes people report only a test result that was significant at a certain level without giving the p-value. It is much better to report the p-value along with a decision on whether to reject it. There are two reasons for this. There's a big difference between a p-value that is just barely small enough to reject it and one that is extremely small. For example, at 0.05 significance level, there was a huge difference between the p-value of 0.049 and the p-value of 0.001. Not everybody may agree with your significance level at alpha, but by reporting the p-value, we let people decide for themselves at what level to reject the null hypothesis. So in other words, someone might say, well, this is not a strong enough number to reject it. We need to maybe reject it at 0.01. And they need to make that decision, like they said, on their own. You need to just report everything that you can so that that decision can be made. When using the critical value method, you should report the value of the test statistic rather than stating whether the test statistic was in the rejection region. This will tell the reader whether the value of the test statistic was just barely inside the critical region or well inside. Also, it provides the reader an opportunity to choose a different critical value and determine whether the null hypothesis can be rejected at a different level. Objective 6, distinguishing between statistical significance and practical significance. So when a result has a small p-value, we say, wow, that's statistically significant. Well, they didn't put wow in there, I added that. It is therefore tempting to think that statistically significant results must always be important. But sometimes statistically significant results do not have any practical importance or practical significance. For example, a new study may raise scores by 2 points on a 100-point scale. This improvement may have statistical significance, but is it the improvement important enough to offset the cost of training new teachers to invest time on behalf of the students? All right, big long list of what we should know from this section. So, what are the assumptions for performing hypothesis tests about mu when the standard deviation is known? How to perform hypothesis tests about mu when standard deviation is known for the critical value method? How to interpret a p-value? How to perform hypothesis tests about mu when the standard deviation is known with the p-value method? How to describe the relationship between hypothesis tests and confidence intervals? How to describe the relationship between alpha and the probability error, and how to distinguish between statistical significance and practical significance. Is it practical or not? And why is it better to report the p-value or the test statistic value along with the decision of a hypothesis test? I always say the more information that you can give, the more transparent you can be, the better. All right, so that was the end of this section. I will see you for the next one.